Next question. You have a retaining wall 8 meter high which retains C5 soil. C is given as 15 kilopascal, phi is given as 15 degree, unit weight is given as 18 kilonewton per meter cube. You are asked to calculate the magnitude of the total positive active thrust against the wall. So you have 8 meter high retaining wall there, and from the value of phi given, you can find Ka, coefficient of lateral earth pressure in active condition, 1 minus sine phi by 1 plus sine phi. Substituting phi equal to 15 degree, Ka turns out to be 0.588. Now, since it's a C5 soil, we know the equation is Ka gamma Z minus 2C root Ka. So the pressure distribution diagram would be like this, with negative 2C root Ka on the top and Ka gamma Z minus 2C root Ka at the bottom. And while discussing the theory portion, we had said that there'll be a point where there's a transition from negative to positive, and at that point you have zero value. That is the height we marked as ZC from the top, and let's mark the remaining depth as Z minus ZC. So at Z equal to 0, or at the ground level, sigma h is equal to Ka gamma Z minus 2 root Ka is equal to minus 23 kilopascal, because Z is equal to 0, so what remains is minus 2C into root Ka. Substituting, you get the value of negative 23. And at Z equal to 8 meters, which is at the bottom of the retaining wall, Ka gamma Z minus 2 root Ka gives you a value of positive 61.67 kilopascal. Now, for us to get ZC value, we can equate Ka gamma Z minus 2 root Ka as 0, right? Because that is a point where Z is equal to ZC. So when you equate Ka gamma Z minus 2 root Ka is equal to 0, you get ZC is equal to 2.17 meters, which means from the top level, when you move 2.17 meter downward, you'll reach the point where the value of sigma h is equal to 0, or where the negative trend changes to the positive trend. So to calculate the magnitude of the total positive active thrust against a wall, you have to find the area of the triangle which is below the dotted line. So the area of the triangle is nothing but the height Z minus ZC into the base width into half. So PA is equal to half into, we know the base width as 61.67 at Z is equal to 8, into 8 minus 2.17, which is Z minus ZC. So solving this equation, you get a value of 179.8 kilonewton per meter run approximately. That is a value of the magnitude of total positive active thrust against the wall. Next question. You have a retaining wall 8 meter high. It retains a layered backfill. Layer number 1 extends to 5 meter depth with unit weight 18, C equal to 0, phi equal to 30 degrees. Layer number 2 extends from 5 to 10 meters with a unit weight of 20, C equal to 0, phi equal to 34. So fundamentally it's cohesion-less soil, and neglecting the water table, you're asked to draw the active earth pressure distribution. So I've drawn a schematic picture here with the pressure distribution diagram. You have the retaining wall 10 meter high. First layer is 5 meter in depth. I've marked this at the layer as AB. It has unit weight 18, phi equal to 30 degrees. And layer number 2, BC, is from 5 meter to 10 meter, unit weight 20, phi equal to 34. Now in the layered backfill theory portion we explained, we had said that the pressure distribution is from 0 to Ka1 gamma 1 H1, and just above the interface you have Ka1, and just below the interface you have Ka2. So at this level, just below the interface you have Ka2 gamma 1 H1. It extends as a surcharge, and it forms a rectangle below that. Plus you have a triangular distribution of Ka2, gamma 2, H2 starting from the interface, linearly varying to the base. So that's the nature of the pressure distribution diagram. So to get the active case, we have to find Ka value for each of these layers, Ka1 and Ka2. Ka in general is 1 minus sine phi by 1 plus sine phi. So we'll start with each level. Level number 1 is the topmost point, z equal to 0 in level A. So at z equal to 0, level A, sigma h is equal to 0 because you don't have a vertical stress, and for the same reason you don't have a horizontal stress. Now the second one is at z equal to 5 meter, which is at level B, and in level B you have two things, level B with layer number 1 and level B with layer number 2, because you have an interface there and you have to consider a point just above the interface and just below the interface. So at this point I've considered the point just above the interface, that's level B in layer number 1. So sigma h is equal to Ka1 gamma 1 h1. Ka1 is 0.33, which is a value that you get when you substitute phi equal to 30 degrees. So 0.33, gamma 1 is 18, h is equal to 5. So you get a value of 30 kilopascal. Now again at z equal to 5, level B in layer number 2, which means a point just below the dotted line or the interface. The difference is that instead of Ka1 you have Ka2, so you have Ka2 gamma 1 h1. Gamma 1 h1 remains the same because that's at that level you have gamma 1 into h1 as a vertical stress. So gamma 1 h1 multiplied by the different Ka2, so 0.28 multiplied by 18 into 5. 0.28 is nothing but the Ka value corresponding to phi equal to 34 degrees. So you get sigma h is equal to 25.5 kilopascal approximately. Now moving on to the third level, z equal to 10 meter, level C in layer number 2, which is at this level. You have Ka2 gamma 1 h1 plus Ka2 gamma 2 h2. In short, you have Ka2 into gamma 1 h1 plus gamma 2 h2. Ka2 is 0.28, and gamma 1 is 18, gamma 2 is 20. Substituting these values, you get sigma h is equal to 53.77 kilopascal. Next question. You have an 8 meter high retaining wall with a 5.5 meter deep sand layer with unit weight 18.5, C equal to 0, phi 34 degrees, overlying a saturated sandy clay of gamma saturated 20.3, C equal to 17, phi equal to 28 degrees. The water table is at the interface of the two layers. You're asked to sketch the active earth pressure distribution. The earth pressure distribution would look like this, and we'll try to see the value of each ordinate. Of course, I have marked level number 1 as level A, then you have level B and level C. So AB is the level or the layer where you have deep sand layer, and BC is the layer where you have sandy clay. So this problem has got a mix-up of layered soil and the presence of water table and a presence of C5 soil. Starting from the top, at z equal to 0 or at level A, you have pure sand. So sigma h is equal to 0, and sigma v will be equal to 0. So you don't have a stress there. And we'll move to the next level, level number 2 or level B, which is at z equal to 5.5 meter in layer number 1. Again, level B is an interface, so you have to consider layer 1 and layer 2 separately. Which means at layer number 1, you have Ka1 and gamma 1 H1. It's pure sand. So sigma H is equal to Ka1 gamma 1 H1. Ka1 is a value that you get when you substitute phi is equal to 34 degrees into Ka equation. Gamma 1 is 18.5 already given. H1 is 15.5 already given. So sigma H turns out to be 28.8 kilopascal. So the ordinate here in level B at layer 1 is 28.8 kilopascal. Now again at level B in layer number 2, you have to consider Ka2 plus layer number 2 is sandy clay. So you have to consider the new equation, that is Ka2 gamma 1 H1 minus 20 root Ka2. Ka2 is a value that you get when you substitute phi equal to 28 degrees. Gamma 1 H1 is the same, 18.5 into 5.5. C is a cohesion value given 17 kilopascal. Again Ka2 is a value 0.361. So substituting these values, you get 16.3, which means at level A it was 0, it linearly increased to 28.8, then it decreased to 16.3 at the same level, and moving to z equal to 8 meter, that is at the bottommost point, level C. The soil is layer number 2, which is sandy clay. So the equation is Ka with minus 20 root Ka2 value, plus you have the effect of water table, because the water table starts at the interface. So the equation is Ka2 gamma 1 H1 plus gamma dash 2 H2 minus 20 Ka2 plus gamma W into H2. Ka2 corresponds to Ka value at layer 2. Gamma 1 H1 is a surcharge load due to AB layer. Gamma dash H2 is a submerged unit weight due to level BC. C is a cohesion value given 17 kilopascal. Gamma W is a unit weight. Solving the equation, you get a value of 50.6 kilopascal. Again, some standard textbooks may separately show gamma WH2 as a right angle triangle, just like the one that we had discussed in the theory portion. Nonetheless, the value will remain the same, 50.6 kilopascal. So like I said, this problem has got almost every variations that we have considered. It has got layered soil, it has got C5 soil effect, it has got the presence of water table. So you need to consider all these complexities while considering sigma H, especially at z equal to 8 meters.